Good afternoon. Welcome to the Operational Research Society's 2020 Beale Lecture. My name's Edmund Burke. I'm Deputy Vice-Chancellor at the University of Leicester, and I'm President of the Society. I haven't been President for long. I started on the 1st of January, and this is my very first public event as President, so bear with me if I make a few mistakes. I'd like to give a very special welcome to Rachel, Marcus and Nicholas Beale, who are the three children of Martin Beale, after whom this award and this lecture is named. They're here as a result of a meeting with one of our very oldest, long-standing members, over 50 years, Martin Fieldhouse, a family friend who shared details of these talks. And we really are delighted to welcome you, to have you here. Thank you. Thank you for coming.
Well, thank you. I must first thank the OR Society for awarding me its Beale Medal. I've not been a very active member within the Society, as I've been mainly interested in specific aspects of OR, like computer simulation, so have participated mainly in societies focused on such subjects. The medal from the Society came as a complete surprise. I'm not at all sure I deserve it, and I'm very humbled by its award, so thank you so much again. As his children, Rachel, Marcus, and Nicholas, are in the audience, let me first tell everyone the story of the only time I met Martin. He was the first person I ever met who rejected me for something I had applied for. I had just completed the Cambridge Diploma in Mathematical Statistics, a qualification I share with Martin, and had applied for a job in Psychon, of which he was a director. Though this was over 50 years ago, I remember the interview well. It was in the morning, quite early. There in the waiting room was the Times newspaper of the day, casually thrown down with a crossword already completely finished. Martin began the interview by showing me a table of the current positions of the football teams in the league, asking me how I might use it to predict their final positions, to which I could only give a feeble answer. He then asked me if I might consider doing a PhD instead of joining Psychon. When I did not rule this out, he spent the rest of the entire interview telling me the downside of doing a PhD. I only hope that the reason he rejected me, and not my feeble answer about football league tables. He then asked me if might, so some of you may be puzzled by the subject of my talk, as it's very far from my research interests, so let me explain how I came to choose it. I was looking at our society's definition of OR as given in our old strapline, the science of better. This seemed to beg the question, better what? I now realize that emphasizing better cleverly implies OR should only be used if decisions can be ranked in order of preference. In other words, OR works best for uncontentious problems. We therefore need to be thoughtful in the use of OR to be clear about the precise objective of a problem and if OR is going to be useful. If so, what choices apply in achieving the objective? And this is what I wish to explore in my talk. I'm in no position to make my decision definitive, so in the time available, I shall simply confine myself to just 4 examples where choice plays an interesting role, of which I have personal experience. So I'm afraid my talk is merely reflective reminiscence rather than cutting edge like Yvonne's. At least it does allow me to describe things I found interesting, which I hope you find entertaining as I did. That was the science of better. Making decisions in dilemmas, when making large things, selling ship handling simulators, and fitting regression lines. The first example is just a warning. Dilemmas, a problem that OR is not good for. OR does not work in a problem where opinions differ in how to tackle it. Such problems are political. The dilemma is such a problem where there are only 2 choices, both of which are unpalatable to someone. In the UK, we're a democracy that works by public consensus, where the winning party is expected to handle the country's dilemmas. The prime example is Brexit. At the end of his 2018 Beale Lecture, I asked Professor Mike Jackson the rather silly question if his highly regarded work on systems analysis could help resolve Brexit. He paused only an instant before giving the one-word answer, no. His answer was spot on. I cannot resist illustrating the point that OR should avoid dilemmas by describing one much simpler than Brexit, in which I was heavily involved for over 6 months, and that occurred in Ludlow, where I now live. The dilemma faced Mr. Colin Preston, the CEO of Shropshire Wildlife Trust, which maintains some 40 nature reserves, with the openly stated mission of conserving the wildlife and environment of each. One such reserve is Whitcliffe Common, which overlooks Ludlow. There it is in green with lots of trees, with Ludlow depicted in yellow on the other side of the team. Officially, the Wildlife Trust is leaseholder of the common. It is, however, heavily reliant on local volunteers, the Friends of Whitcliffe Common, a charity whose work maintaining the common is much appreciated, but unfortunately not invariably. Some members of the Committee of the Friends, including its chair, think that having too many trees spoils the view of the town from the common. There are minutes of the Committee of Friends dating back to 2013 that discuss felling 2 prominent 55-year-old oaks, which the chair realized would be highly controversial when the only minuted reason given for felling was view enhancement. Well, there's a view. And there are the 2 trees in question. There's a view in winter, trees there again, and one I took when this dilemma blew up with the church tower, St. Lawrence, in between. In March 2016, the Friends Committee finally asked Preston to fell the oaks, which he agreed to. This only needed the Wildlife Trust, as leaseholder of the common, to submit a notice of felling to Shropshire County Council. The notice would have been disallowed if the County Council had objected, but they did not. They didn't want to oppose the trust. And the notice of felling became operative automatically in August 2016. However, many Ludlowians had objected, including Ludlow Town Council, unanimously. The Friends Committee therefore wasted no time in demanding Preston fell the oaks. As the originator of the notice, he could still have stopped the felling simply by withdrawing the notice, as this only allowed the trust to fell, but did not require it to do so. Those, including myself, who were against the felling, mounted a public campaign against the felling. We were well supported by the Ludlow Advertiser, the local newspaper, who printed many letters of condemnation, including the unequivocal opposition of Dr. George McGavin, a well-respected Oxford entomologist, BBC 4 broadcaster, and admirer of the oak, whom I had alerted. Preston was in a dilemma. After 6 more months of heated debate and meetings, he proposed a compromise: fell just 1 oak. This pleased nobody. This was in February 2017. So there's the oak set for chopping down. This one on the left. And there's my picture of it with it sort of ringed. However, before even this proposal was discussed, subcontractors, who were non-local, as no one local would do it, came at dawn before anyone was about and cut down the 1 tree. I admit there is a much better view of the ruined castle. I don't think OR could have helped in that dilemma. There is, however, one interesting dilemma where OR can play a part: those that involve reducing risk. A risk is a random event which, when it occurs, is not pleasant. Suppose a risk can only affect a very small number of people, but for whom the consequences are dire, like death. Suppose also that the risk can be removed entirely, but where most of the population would find the means of removal tiresome, though only slightly so. Does one remove such a risk or not? An example is where roller-blind pull cords are now made to immediately break if tugged too hard. The decision in such a dilemma is helped by reliable statistics. In the UK, there have been about 1 or 2 deaths a year. Though I find the new form of poor courts tedious, perhaps one should put up with them. A consensus decision, however, is needed, so perhaps should be left to government. In his Wreath lectures last Christmas, Lord Sumption discussed the legal aspects of similar dilemmas, where the risk level can be adjusted, but any reduction must be weighed against a loss of individual liberty, setting road limits, for example. The Fire and Rescue Service, when it was under the control of the then Office of the Deputy Prime Minister, retained me to study its effectiveness when dealing with life-threatening incidents. I was asked to value a life saved at £1.3 million. So OR is used in government financial appraisals of risk involving life and death. So that's my first item. Next one is making large things. When making large things, OR offers a powerful tool, discrete event simulation. But it's not always used. I had a student, Joe, who worked for Swan Hunter, the shipyard in Wallsend, but had been sent to do an MSc in Cardiff, where I was. He chose as the topic of his summer project discrete event simulation of the building of very large crude carriers, VLCCs. And I went up to Tyneside to see him and a VLCC being built. So there's the picture of the VLCC. I'm not sure if it's the actual vessel I saw being built, but it was round about then in the late 70s when we still manufactured such vessels. They're large, over 250,000 deadweight tons and 330 meters long, so that's 3 football pitches. In fabrication, in fact, I must tell you what happened when I went to visit the shipyard. I was amazed, actually, to see that the vessel was so large that its bow jutted right out over the road approaching the shipyard. In fabrication, the keel is first laid in a construction dock, and the vessel is then built up progressively from units, each of about 100 tons. I mean, for comparison, a large articulated lorry nowadays is just 44 tons. The units are assembled simply in a fabrication shop before being moved to the dock for final welding into place. You can imagine that once a unit is started, you do not want to move it about unnecessarily. So DES is needed to determine when and where to make each unit. What can go wrong if you do not simulate such a manufacturing process first? So that's where the A380 Airbus wings comes in. Back in 2003, I was invited to join a team to visit Broughton in North Wales, where the A380 wings were being manufactured. Airbus wished for advice on how to improve the manufacturing process. I no longer have our report, but what stood out was that either DES had not been used in the first place, or if it had been used, had not been sufficiently thorough. Several production clangers might then have been avoided. I'll just give 2 examples. This is the internal framework of a wing. That itself is just 37 meters, nearly 2 cricket pitches. Here's the outer skin being readied on a so-called washing line for riveting to the internal framework. Notice here the, I need to be careful with this, the little triangular piece sticking down. The riveting machine is 250 tons, but it actually rivets to near micron accuracy. The riveting machine controls are all keyboard controls, very simple. However, here's the outer skin in place, ready for riveting, and notice how high it actually is. It's so high, the top lines of rivets are not reachable by the riveting machine. Even when standing on working platforms, riveting men could not reach them. The platforms have guardrails to prevent the men from falling off. The men instead had to stand precariously on top of the guardrails to reach. Roundabouts constructed to take the wing from the factory that you can see there were too small for the wings to go round. Fortunately, there's a field behind, and there's a sort of canal there. So what actually happens is that the wings sort of take out over the field and barged out instead of being on the road. So the moral of this is that D's planning is really useful in such manufacturing. Ship handling simulators. I want to tell you about my involvement in the early development of low-cost computer-generated imagery, CGI, for ship handling simulators. They're the marine equivalent of flight simulators. I'll describe this in a little more detail than relevant for this talk, mainly to fill you in on something I was engaged in for some 15 years that I'm not particularly known for. I hope you find the area of interest in its own right. It does, however, tie in with the main theme of my talk in providing examples of the importance of choice in marketing strategies when taking account customer thinking and psychology when trying to sell such products. I had bought a BBC Micro in the early 80s, finding it had surprisingly good graphics, given it only had 32 Ks of memory, 32 KB of memory. Compared the old notebook that I prepared these slides on with its 6 gigabytes of installed RAM. That's what, 6,000 million bytes. I made a ship handling simulator for a tabletop. It had instrumentation, radar, CGI, night and day, and I showed it to Dr. McCullum. He's there, sitting there, a colleague at Cardiff University. He already had a company, Maritime Dynamics, that marketed differential equation models simulating the motion characteristics of different actual ship types, ranging from fast attack craft through to VLCCs. I'd incorporated such motion equations in the simulator. They were very primitive. It therefore achieved its main role of reproducing vessel maneuvering characteristics accurately. Ian found Dr. McCullum found a market for this product both in the United States and UK. There was nothing like it at the time. I then acquired a BBC Archimedes Micro, the successor of the BBC Micro. This was based on a reduced instruction set computer processor, a RISC processor. It's a forerunner of what is now used in practically all modern smartphones. So you've probably got one of the ARM processors in your smartphone. And with that, I was able to produce a nocturnal CGI system that Maritime Dynamics called Martin Vision. And if you're into your night, you can see that some of the vessels are going to port, some to starboard. Maritime Dynamics made a very eye-opening, successful sale of Martin Vision. The Naval Cadet College in Plymouth was in the market for a CGI system to be used for nocturnal navigational training. However, it was known that the commanding officer of the college, a Captain Jestico, was very suspicious of what he considered newfangled computer-generated visuals as opposed to training cadets in real vessels. 2 companies had, however, been shortlisted. One was Maritime Dynamics, the other, a much more established company. I think it was Rayco. Anyway, let's say Rayco. They were the first to demonstrate their ostensibly far superior CGI system to Jestico a week or 2 before Maritime Dynamics gave its demo. Rayco got their demo seriously wrong. They tried to show off their CGI without considering how it would be used. Their demo was far too flashy, with helicopters flying about. Jessica was reported as coming away muttering computer games. I attended the demo that Maritime Dynamics gave. We had someone, Dr. Ian Ringrose, whom I knew well, in charge. He had seagoing experience and a mariner's qualification. When Jessica arrived, Ian first informed him we would be simulating approaching Calais in a ferry at 4 knots, providing him with something he understood, a chart of the entrance to the harbour. I could see Jessica adopt his sea legs as he went onto the darkened simulated bridge. Ian had cunningly placed a fan to reproduce a slight breeze. We had a helmsman, Mike, also a former mariner, who played his role by responding to Ian's instruction with, "Aye, aye, sir." I knew we had the contract won when Jessica, after peering at the screen projection for some minutes, said, "I need my binoculars. I think the stern light of that vessel ahead is slightly too bright." Maritime Dynamics was awarded the contract. And I want to describe the work Ian and I subsequently did for Norcontrol, a Norwegian company that was the world-leading manufacturer then of radar simulators. Norcontrol wanted to turn these into full-mission ship-handling simulators by adding CGI, but sufficiently cheaply to be affordable for maritime training institutions. The work I did for Norcontrol confirmed two things. First is the obvious fact, which any young researchers, or any young researchers here, should, but does not always take note of, that it is much more enjoyable and rewarding to contribute to a newly developing field than one that is already well worked over. Secondly, it showed Norcontrol was able to take advantage of what was then a rapidly improving new technology much more quickly than Maritime Dynamics, as Norcontrol was a much larger company, and moreover its size allowed it to adopt selling strategies that Maritime Dynamics was unable to match. Norcontrol engaged Ian, me, and a research student to develop a CGI system, subsequently called Norview 90, a transputer parallel processing microprocessor we used for that. They sold their first full mission simulator to the powerful Siemens Church Union in New York. So that's why you've got the view of Manhattan Line, where still the Twin Towers were still in existence in those days, and there's the Statue of Liberty. So Joseph did all the data development work for that. Diverse uses for ship handling simulators opened up. For example, in the training for offshore oil loading. This slide shows how oil is obtained offshore. I don't think it's done always like this nowadays. It's less risky to pump oil from the oil into oil rig to what's called the single point mooring there, and then it's delivered to the vessel close by, which you can see in the picture. There's in this close-up, there is a hawser tension to hold the vessel close to the single point mooring, and then the oil hose there as well. The captain of a vessel being loaded must be able to handle rough conditions like this. Norcontrol had the opportunity to upgrade the obsolete existing cinefilm visuals of a simulator in Trondheim, which could only be used for training to sail up certain fjords, presumably those are the ones they had cinefilm for. With CGI, training in offshore oil loading would be possible. Unfortunately, Norview 90 was not good enough. Ian and I, with two further colleagues, Andrew and Peter, developed a new CGI system for Trondheim called Norview 2000. And there it is, set up for training in offshore oil loading. You can just about see the SPM in the visuals, and some of it at the front might be able to make out the hawser and the oil hose, which all had to be simulated accurately. The background to the installation was quite interesting. Here's Pete in Trondheim installing the system. You see at the front there quite a number of Spark workstations used to drive 7 AT&T Pixel machines, for which you can see in this picture. Those are the black things that you can just about make out. We used, I should perhaps tell you that I actually developed the CGI code for the Pixel machines, but I had to go with Ian to New York to buy the hardware from AT&T. We used the strategy that Norcontrol, being Norwegian, was the only company likely to be allowed to replace the Trondheim visuals, and then only if the price was right. The Pixel machines were utterly obsolescent. AT&T offered us the 7 machines we needed for £1.1 million, what they considered a generous discount. Ian beat them down in the end to 220,000. The simulator itself was pretty good. 7-meter projection screen here with a 27-degree wraparound. Oh, this has nothing to do with the talk, but the view from Trondheim simulator rooftop was rather nice, so you can have a benefit of that. That's Pete in there looking out. This is Norview 3000. It's a depiction of Dover Harbour. I wrote the computer code for this, for anti-alias rendering, texturing, C-wave animation. This used the Intel i860 graphics processor, a new chip then that in computing speed was a modern cheetah compared with the AT&T Pixel dinosaur. The technical quality of the product is important, but the psychology of marketing is the key to success for the company. Here's an example. The Port of Singapore Authority wished to acquire a ship handling simulator for training its port pilots. They drew up a short list of 3 manufacturers, including Norcontrol, and I was actually flown out to Singapore to make a presentation for Norcontrol's CGI. Various aspects were covered in the presentations, with all bidders describing how they dealt with an aspect before everyone moved on to the next. The CGI presentations occurred early, and I remember the audience included many senior PSA executives who seemed to be paying very little attention to the CGI presentations. Clearly, PSA had only shortlisted bidders whose simulators they were happy with, so that all our technical presentations were actually superfluous. We were followed by the 3 presentations describing financial considerations, whereupon the PSA executives all woke up. This was what they were really interested in. One company was proposing deferred payments so that PSA had to find little cash up front. The Norcontrol presentation was even more clever. It was a piece of financial engineering. Norcontrol recognized that PSA would want to offer simulation courses, widely promoting the Port of Singapore as a whole. So Norcontrol's proposal was to give their simulator for free to PSA, but in exchange for a share in offering courses, thereby including Norcontrol in any future successful simulator use. Norcontrol could adopt such a selling strategy as it was financially backed by 3 big-hitting Norwegian parent companies: Broughton's, then Norway's largest domestic airline, Aker, a fuel exploration company, and Statoil, the big Norwegian oil producer. In comparison, Maritime Dynamics products were equally innovative. I was involved with the construction of this very realistic crane simulator, where we had a very bright research fellow writing the collision detection code. Quite tricky, that. Once I mishandled the crane, dropping the simulated container, and it crashed and bounced off the vessel with impressive realism, including sound effects. I myself reprogrammed the Archimedes visual chip for Maritime Dynamics to produce a simulated radar signal for use with a real radar. So that's a real radar displaying the signal that I sent to it. But Maritime Dynamics did not have large financial backers, so difficulty selling its simulators and surviving. As is so evident nowadays, financial muscle is crucial in maintaining one's position in the marketplace. Right, I'm now down to something a little bit more sort of technical. Non-standard regression model fitting. This involves my academic research. It illustrates how inappropriate choice of a statistical model can lead to unexpected complications. I encountered such examples in the 80s, explaining them in published work, only to find that even relatively recently, they were still puzzling some people. This led me to write my book, Non-Standard Parametric Statistical Inference, published by OUP. My example allows me to advertise the contents of the book to encourage some of you to dip into it. OUP are kindly offering a special discount of 30% to anyone attending this lecture who wishes to buy my book. And there are flyers dotted around here and in the coffee area. So if you like to pick one up, you get a nice 30% discount. The example is, I hope, not too unfamiliar to anyone, whether you're into statistics or not. We're trying to explain how a numerical quantity that we're interested in, y, say, is influenced by a so-called explanatory variable, x, doing this by fitting a regression line. Here are three observations which I put on a graph, x and y, the data, and these are made-up points. If we need an explicit example, a research student friend of mine who worked for an agricultural research station wanted to estimate the weight of quality meat in a bullock, an abattoir job if you're going to do it properly. This would be our y. Instead, he wanted a way that did not involve slaughtering the bullock, like measuring the width of its tail. This would be our x. So if reliable, x could then be used to predict y. In this example, the 3 points look roughly in a straight line. And mathematically, a straight line is just y is equal to a plus bx. The a and b are what are called parameters. And in this straight line example, they can be calculated by known formulas. You don't need to know what the formulas actually are. Here, in fact, they gave a minus 0.44 and b 1.5, and that was the line it actually produced. So no problem fitting a straight line. We've got known formulas for doing this. What about fitting a curve? Let me just extend that diagram a little bit to the left are just the straight line that we saw before. On the right, the best point I've displayed here, there, in what's called parameter space, where I'm just looking at the parameters on their own. So the point of this is just simply to indicate that how the parameter point gives rise to the fitted line. What happens if you're in a situation where explicit formulas are not available? Well, we can then actually use this parameter space in a different way, which is more general. It's, as I described here, what we do is we search different points, A, B, in the parameter space. At each point, we calculate something that's easy to calculate, the likelihood. That's the L. And the key here is that the likelihood is just a measure of how close the line corresponding to AB is to the observations. The larger the likelihood, the better the fit. So the best point, therefore, is simply the point that corresponds to where the likelihood is largest. I've drawn the contours. If we were able to, perhaps I ought to go back a moment, if we were able to actually calculate the likelihood throughout the actual parameter space, we could then actually produce what I've called, what I would think of as being a map with the contours of the likelihood where the height is equal. And you can see, in this case, they're sort of oval-shaped, and the best point is that one in the middle. That's where the B is 1.5 and A is minus 0.44. And it's something which we then find not by an explicit calculation, but we can start anywhere in this diagram and just simply move in the direction towards increasing slope until we actually always invariably end up at the top point. So hill climbing handles this problem perfectly so nicely. How about fitting a curve? Now, I've chosen a simplified Herschel-Balkley line. Don't worry about the mathematical details. I'll tell you why I've chosen this. It was actually a problem that I helped my oldest brother with. He was a government research scientist, a former president of the Rheological Society. Rheology, I don't know if we know, involves the movement of non-Newtonian fluids. He was in much demand concerning problems where industrial amounts were being handled of substances ranging from concrete, mud, glues, dough, as in baking, making tons of dough, chocolate. So if you ever have a Cadbury's chocolate bar with nut in it, he was involved with making sure you had enough nuts in each bar. And lipstick. He analyzed the flow of such fluids, fitting the Herschel-Balkley line to observations where y is then actually the shear stress and x the shear rate. don't worry about the mathematical notation in this. You only need to know one thing that's rather unusual about the HB line. In the straight line, you see, y is a plus bx. If you estimated a as being 0, then y is just simply equal to the estimate of b times x. If, on the other hand, b was 0, then y is just simply the estimate of a. However, if you look at the HB line, something rather strange happens. If you estimate a as being 0, then it so happens that the term in the round brackets here is always identically equal to 0, because it's actually 1 minus 1, whatever the value of x. So b multiplying it is knocked out. So y is then 0, and b doesn't really exist. Likewise, if b is 0, then it clearly knocks out the term in the round brackets, so a no longer exists. And what happens then if you try and estimate both simultaneously? So no, that's the actual sort of technical sort of problem involved. Well, I'm not going to tell you about the mathematical nicety of this. Instead, what I'll do is to show you non-mathematically what happens if you try to fit the HB line using hill climbing. If we started with values a and b, well, actually, what happened was that I actually had to stop the hill climbing because it was quite clear that a seemed to be drifting to 0 and b was blowing up. And if you actually look at the line, it sort of fits, but it's not as good as our previous straight line. If, however, I use the starting point a is minus 1 and b minus 1, then the hill climbing worked perfectly well. A ended up at minus 0.2 and b at minus 5. And you can see it's actually picked up the curve very nicely that you might not have noticed before. Well, what's happened here? Well, you can actually see in the likelihood plot that, in fact, we've actually got two boomerang-shaped ridges, one down here in the lower quadrant and one high up in the upper quadrant. And if we started, as I did when A and B were both minus, we were in this lower quadrant, and the hill climbing would then automatically move up nicely to the correct maximum. If we started over here, when they're both positive, well, this ridge, in fact, doesn't have a finite maximum in this picture. It actually rises gently as b tends to infinity, and the maximum we finally get there is when b is infinity, and it's actually an inferior maximum. So it's actually not worked out at all. I mean, this is a pretty simple example, and really this is happening. What can we actually do about it? And this is where the mathematics comes in. Instead of the Herschel-Berkeley line, and that's the top thing, let me just do a little magic conjuring trick. I'm going to multiply that by A, and now immediately divide by A, so that clearly doesn't change anything. The A's cancel out. But what I'll do, instead of having B as being a parameter, I'm going to call C, which is A times B, a new parameter. And I'm going to plot the likelihood as a function of A and C instead. And lo and behold, the problem disappears. So you have to know a bit of maths to see exactly how I did that, really. But there is a sort of ridge, but there's a clear maximum, and it's in the right place. A is minus 0.2, C is 1, and that translates to B being minus 5. Well, there are lots of examples like this, systematically set out and explained in my book. So I encourage you to look at that if you're at all interested. So on that triumphant note, I will end my talk. Thank you very much.